right, good morning, Lisa and Paige. So today these are your notes over section 2, 5. So yeah, chapter 2, section 5. It's all about continuity, and sorry these get a little bit long, but we were going to spend 3 days on them, so just bear with me as we kind of go through these, okay? Okay, so first of all, continuity, what it is talking about, we'll talk about points and lines and like whole functions and everything. But so a continuous function, just long story short, it can be sketched over its domain in one unbroken motion. So if you can take your graph and you never have to pick up your pen or pencil and you just draw a line and your whole graph is graphed, that's going to be a continuous function. Okay, so it's all just one motion, like there's no breaks in it. So looking at this graph, it says at which numbers does the function appear to not be continuous? So anywhere that we have a break in the graph, it's going to be not continuous. So we can see right here, when x is 1, I approach 2 different values. So I would be not continuous at x equals 1. Okay, so I'll just write these down. So at x equals 1, I'm not continuous. Also, as I move it along, when I get to x equals 2, I have a point up here and then an open circle right here. So at x equals 2, I'm not continuous. Okay, so also at x equals 2. Going along, I can keep drawing without having to lift my pencil up. Oh, but then at x equals 4, I have to make a dot down here. So in order to get down there to make that dot, I'm going to have to lift up my pencil. So I would be not continuous at x equals 4 as well. Okay, so anytime you have to pick up your pencil and move it to start graphing somewhere else, it's going to be not continuous. So then we have different types of discontinuities. Jump discontinuity is just going to be where the graph appears to jump. So the left hand and the right hand limits approach different numbers. So looking at this graph right here, so as I'm going along, when I get to x equals 1, so my line is doing this, but all of a sudden it jumps up here, and now I'm doing something else. Okay, so we would have a jump discontinuity at x is 1, okay? So anytime I jump. And then a removable discontinuity, that would be if I can actually remove this discontinuity by changing the function value at that one point, and then it would make a continuous function. So if I changed my function value right here, so if I took this point that's up here at 2, if I changed that function value and instead made it at 2, 1, then I would have a filled in circle right here, and all of this would then be continuous. And the same thing over here at 4. Okay, so for at 2 and at 4, we have removable discontinuities, because basically if I just change this point, I can remove the discontinuity. So I could remove this point, put it right here, and that would fix my problem. But the jump discontinuity, I can't like remove anything or change it. That's just when the graph jumps from one, it's doing one thing, then it jumps and it's doing something else. Okay, so those are our different types. Okay, so then we also can talk about continuity from the left hand and the right hand side. So basically if we go through this, it says, so C, let C be a real number that's either an interior point or an endpoint of an interval in the domain of F. So the endpoints, the points, if our domain, like on this graph, we're just going from 0 to 4, those are our endpoints, so they don't have to be continuous from both sides. They only have to be continuous from the one side inside of our domain. So a function is going to be continuous if our limit as x approaches some value of c is equal to what the function value of c is. So if we look at our graph for an example like that, so if I look at when my x is 3, my limit at 3 is going to be 2, because both sides of our graph, as I'm limiting it in, are both approaching 2. Okay, so, and because the limit is 2 when x equals 3, and also my function value, so when f is 3, I have the value 2, so I would be continuous right there. Okay, so you're continuous if your limit approaches the same number that it truly is on the graph, that the function value really is, okay? Then right hand and left hand, so that just depends on which way we're approaching. So it says a function is right continuous at C, or continuous from the right. So if I'm coming from the right side, so again, it's just like how we do it with limits. So it would be as the limit as x approaches C from the positive, so plus from the right side. If I approach whatever limit it is, approaches the same function value, then you're right continuous. So if I look at, let's look at the point when x is 1. So here I am at 1. So my function value, my filled in point, is at 1, 1, okay? So when I'm at 1, the point on the graph is at 1. So that's my coordinate, that's my function value. Then my limit, when I'm coming from the right-hand side, so when I'm coming from this way, I'm limiting. So my limit when x is 1 is also going to be at 1. So the point x equals 1 would be right continuous. It would not be left continuous because the function value is at 1, but the limit from the left side is approaching 0. So that point right there, it's not continuous, like overall, it's not continuous. It's just right continuous, okay? And then left continuous would just be the exact opposite. So if you're approaching some number from the left side, your limit and the function value have to be the same. Yeah, so basically, left hand, you approach from the left side, the limit on the left side and the function value are the same. Right hand, the limit from the right side and the function value are the same. And if your limit from both the left and the right both work out to be the same number, they're both the function value, then you're just overall, you're just continuous. Okay, so you can be left, right, or just a general continuous, okay? Okay, so then continuity over an interval. So it says a function is continuous over a closed interval, so from A to B, so a closed interval. If it's right continuous at A, left continuous at B, and then just general continuous at all interior points of the interval. So here I have a picture. So here is my domain of this graph down here. So I'm going from A to B. Every single point in here is continuous, just because all of the function values and the limits are all going to be exactly the same. And then my points on the end, I don't, because they're like the end points. So the one on the left side, as long as I'm continuous from the right, that means I'm fine. And then my one on the end over here on the left, as long as I'm, or on the right, the point on the right, as long as I'm continuous from the left, that means that whole function would be continuous over that interval. Okay, so your endpoints, they don't have to be continuous from both sides, because obviously if it's on the end, you're not gonna have something farther to the left, because this is as far left as it's gonna go. Okay, so I would only need to be continuous from the right because I don't have anything else on the left. Okay, and then just a little side note on my asterisk, it says a function can be continuous, right continuous, or left continuous only at a point for which our function is defined. So anytime we have like those open circles, so if I had a graph like this, but I have like an open circle in here, my function would no longer be continuous. Every single point has to be defined in order to be continuous. Okay, so when you see open circles, you can automatically know that you're not going to be continuous. Okay, because obviously that's a break in the graph. You have to pick up your pencil in order to draw that, so it can't be continuous. Okay, so unless every point's filled in, it's not going to all be continuous. Okay, so looking at just continuity over an interval. So our first example, it says determine if the function f of x is equal to the square root of 4 minus x squared is left continuous or right continuous at x equals -2 and 2. And so I have the graph of that right here. So here's our graph of that square root of 4 minus x squared. And it asks me at -2 and at +2. So if I look at this point, let's start with the -2. So I'm looking at it, so left continuous, I'm coming from the left side. Well, there's nothing coming from the left side, so I would not be left continuous at this point, -2. But I am, however, right continuous, because as I'm coming from the right side, I have a function, I have that graph. So I would be right continuous at -2. And I am right continuous because the limit here, the limit approaches from the right as so my limit as x approaches -2 from the right side is going to equal 0. Okay, so my limit here is 0, and then my function value as well. At the actual, if I plug -2 into my equation, I would end up getting 0. So because those are the same, I have a function value there and the limit, they're the same number. I know that I have the continuity, but I only have the continuity from the right side because I don't have anything over here on the left. Okay, so then at x equals 2, if I look at this point right here, I know if I'm looking from like the left, here I come from the left side, I have the graph right here, so I do have the continuity from the left, but from the right side, here I come, I don't have anything over there, so I would be continuous from the left over here, so from the negative side. And that works out because my limit as x approaches +2 from the left side, so with my minus of my function, is going to equal 0 there. And then also, if I plug that in, or even just look at the graph, I know that the function value at +2 is equal to 0. Okay, so those are the same, so I have the continuity. Okay? Then my other example, this function, it doesn't even have an equation, it's just called u of x. But it says, let's look at x is 0, and let's talk about left continuous or right continuous. Okay, so let's go ahead, let's start with this one. So left continuous, so here I have a function from the left side, and I'm approaching 0, but because I have an open circle on 0, I have an open circle there, so I don't have an actual like function value right there, because if I look at this, I know that my function is defined, so when I'm at 0 on my x, it shows me that it's defined because it's filled in up here at 1. Okay, so when x is 0, y is going to be 1. So my f of 0 is actually 1. So then if I look, so if I'm limiting x to 0 from the left-hand side, so as I'm looking at my graph, when I'm coming from the left-hand side and I approach 0, my y looks like it's approaching 0 as well. So my limit there from the left side would equal 0. Now, because these are not the same numbers, I am not continuous from the left side. So no left-hand continuity. So no left continuity. But from the right side, so I already said that I have the function value, so my f of 0 is going to be 1. And then my limit, because as I'm limiting from my right side, as I'm coming in, I'm approaching 1 as well. So my limit, so I know my f of 0 is equal to 1, and my limit as x approaches 0 from the right side is also going to be 1. So now because those numbers are the same, I do have the right-hand continuity. So I do have right continuity. Okay? All right. Okay, so then just the continuity test, so to determine if continuity even exists, we have to have these 3 conditions. So it says a function is continuous at a point C if and only if these 3 conditions are met. So the first one the function value has to exist, okay? So I've been saying this over and over, but it has to be a closed circle. It can't be an open circle. The function value has to exist. There has to be a point there. So that's the first thing, and it has to be in the domain. Then the next thing, the limit at that point also has to exist, okay? Because we talked about limits in other sections about them not existing. Well, the limit has to exist. And then the third thing is that limit and that function value, they have to be the same, okay, in order for continuity to exist, okay? So you check for your limit, check to see if the function value exists, check to make sure they're the same, and if so, you have the continuity. And then on the bottom, it does say, when we're talking about the one-sided continuity, the left and the right, like we just talked about, then these steps 2 and 3, they're gonna be replaced by like the specific one-sided limit. So like step 2, so if your limit as x approaches c from the left exists, well, then the function value from the left would also have to exist, kind of thing, okay? So same exact 3 rules, just check, make sure it's either like overall in general or left or right hand, or whichever one you're talking about, okay? But it's the same 3 rules. Okay, so then looking at these graphs, we're talking about the discontinuity, sorry, sometimes I struggle with that word, but the discontinuities, those, remember, they're gonna be like holes, asymptotes, any break in our graph. But we want to determine if each of these graphs is continuous or if I have a discontinuity at x is 0. So if I look at this picture A, I have just this straight line. I have a filled in circle when x is 0. So I would say that this line is continuous just because I can draw it all in one stroke. If I look specifically at 0 like I'm supposed to, I have a filled in point and my limit at that filled in point are going to be the same, because at 0 I'm at 1 for my actual function value, and then as I limit from the left hand and the right hand side, I also approach 1. So all of that is the same. So for A, I would be continuous. Now for B, if I'm over here, I have this hole right here. So I know that I can't be continuous at x equals 0, because I have a hole right there, because I need the function value and I need the limits to be the same. Well, I have the limit, but I just don't have the function value. If I did, however, fill in this hole, then I could be continuous, okay? So I could fix it, just fill in the hole, define that value right there, then I could be continuous, but in this case, I'm not. So then for C, again, we have that hole right there, but this time we have a point up here at 2. So for this one, my line, and at my specific point at x equals 0, I'm not going to be continuous just because that point and my hole are not the same. But if I change my function value, like I said before, if I were to move this down here and fill it in, I could make this one continuous, okay? So we'll get into that a little bit later, like making a function continuous after it's like not continuous. But yeah, so if you were to move that value, we could make it continuous, but the way it is right now, we would say that we have a discontinuity at x is 0. Okay, so then for part D, I'm looking right here. So here I am at x is 0. Well, I have an open circle here and a closed circle here. My function value is up at 1, but my limit is gonna be, my limit is 0 from the left and 1 from the right. So because I'm not specifically asking you about left hand or right hand, so in general, you would say that this one is like not continuous, okay? So unless it specifically said like, is this continuous from the right? If I asked that, you could say it was continuous, but because it just says, is it continuous at 0? You have to take into account the left and the right hand, so unless it asks for both, you have to look at both of them. And because the limit for both is not the same, we're gonna say that that one's discontinuous, okay? And if we think back to like the types of discontinuities from like slide 2, this would be a jump discontinuity. So it jumps from here, and then it jumps up here and continues the function, okay? So going down to E, this one, I'm gonna have some asymptote in here. So as I'm approaching 0, I have this asymptote. So obviously I can't have like a function value there because there's an asymptote. And I don't like my limit, it's gonna approach infinity and everything like that. And we'll talk about limits at infinity in the next section. But so this one, so if you see something with an asymptote, you're not gonna have continuity there, okay? So, because there's obviously no function value there. So that would be the reason that we couldn't have that one. And then for the last one, for F, we kind of talked about this in previous sections, but it oscillates so fast, goes back and forth so fast, that I can't have a limit there. So because I can't have the limit part, I can't have the continuity, okay? So that would be different types of just discontinuity. So we talked about like the removable, we saw an example, a jump. We also have like asymptotes and then the oscillation. So all of those like different things can affect the continuity, whether you can have a continuous function or not, okay? Okay, so up until now, we've been talking about like looking at specific points on graphs and figuring out if it was continuous at that point or not. But now we're gonna look at a whole function in general. So a continuous function is a function that's continuous at every point in its domain. So we would have to look at every single point, make sure every single point is continuous, and that would be a continuous function. Or if you can just draw it all in one motion without picking up your pen or pencil, then it's going to be continuous, okay? Discontinuous would obviously just be if there's a discontinuity at one or more points in the domain, okay? So if there's a break in the graph, a jump in the graph, oscillating, the removable discontinuity, any of that stuff, if that appears in asymptote, any of that, you're obviously going to have a discontinuous function, okay? But the only thing I want to point out is, okay, so a discontinuous function, like I said, if it has all of that, that I just listed off, it says, so if the function is discontinuous on one or more points of its domain, okay? So this is specific, like each function has a specific domain. If we think about like parent functions, so you have to compare what you're given to like the domain of, like, so the domain of like what you're given compared to the domain of the parent function. If they're the same, you could still be continuous, okay? Sorry, this little blurb was a little bit bad. I didn't explain that very well, but let's talk about it with the reciprocal function. So our reciprocal function, we know, usually looks like this. So here's our reciprocal function. So it says, is this a continuous function? Well, technically I'm going along and I have an asymptote right here. So we know that asymptotes are going to be discontinuities, but because every single reciprocal function looks like this is the type of function that it is. It's not something that it's just part of that problem. It's like the fundamental nature of a reciprocal function has asymptotes, okay? It's not like we just all of a sudden have one this time. So because the fundamental nature of this has asymptotes and its domain is always, we know that its domain would be negative infinity to 0 and 0 to infinity. Well, the domain of that includes that asymptote. So this would actually be a continuous function. Okay, so a reciprocal function is going to be continuous just because that's how they are. Like, I can draw it in one motion, like each branch. If I had like holes or like another extra asymptote, say there was like, for some reason I had an extra asymptote in here, then that would be discontinuous. But the basic reciprocal function, because the way it is, the way the function is it has an asymptote right here. So that would be like a continuous function. Okay, so I know that's kind of confusing because it breaks the rules of what we were talking about before. But so if the fundamental nature of it is one way, then compare it to that and then think about like, okay, just every function is continuous from the get-go unless you add something to it. If you add a whole to it, if you add an extra asymptote, okay? So compare it to the original function, and if you added something to it, added a discontinuity, then it would be discontinuous. But if it looks just like a normal reciprocal function, then that's gonna be just like, it will be continuous, okay? If you have questions on that, I can probably explain that better. Sorry, but that was bad. Let me try again. Okay, so aside from my reciprocal function tangent, now if we have two functions, so all of these properties are gonna apply. So if I have two functions f and g and they both are continuous, then I know that when I add them, subtract them, multiply them, divide them, I'm also going to have a continuous function, okay? So you can take two continuous functions and like do any algebra on the function, and you're still gonna have a continuous function, okay? The only thing is with the dividing, your like the denominator can't equal 0, so you'll have an asymptote there, just depending on the function. So then that one, it just depends on the case. We'll get into that, but some of those will be continuous and some of them won't, okay? So basically, two continuous functions, you can do anything to them and it's gonna make a continuous function, except the quotient ones, because we have to watch out for our denominator, okay? So we just have to look out for the dividing ones. Okay, so to do an example, it says given the following equation, so I have f of x is equal to 2x squared plus 7x plus 8. And then our g of x is going to be negative 11x plus 3. Okay, so first of all, it says determine if f plus g, and then we're gonna do f divided by g are continuous. So let's do f plus g first. So let's go ahead and find that function. So if I just add these together, I'd have 2x squared, then 7x and negative 11x is gonna give me negative 4x, and then 8 and 3 would give me 11. Okay, so I'm gonna have this function right here. So now if I think about this, if I think about them just in general, so my f of x function, the domain of that one, we know that it's gonna be a quadratic that opens up. Its domain would be from negative infinity to infinity. And then this one over here, we know that this one's gonna be a linear function that's just going down because it has a negative slope. So its domain would also be negative infinity to positive infinity. Okay, so all of those have everything for its domain. It's continuous over its whole domain, because that quadratic, I don't have to lift up my pencil or anything. That straight line, I can draw it just going down. So those are both continuous. And then if I think about this function right here, so 2x squared minus 4x plus 11, that's also gonna be some sort of quadratic. I can draw it all in one smooth motion. So because that one was continuous and this one's continuous, I know that this one is going to be continuous over my domain, which my domain for this one would be negative infinity to positive infinity as well. Okay, so because those two were both continuous, I know that this one's going to be continuous, okay? So for my f and g, it's also a continuous function. Now, if I want to do my f minus my g, or not minus, sorry, f divided by g, okay? So I'm going to take my f of x equation, so I'd have 2x squared plus 7x plus 8 divided by my g of x equation, which is negative 11x plus 3. Now the thing is, we know we can't divide by 0, so I can go ahead and solve this and figure out like what my denominator what value I could plug into my denominator to make that 0, so I know what it can't equal. So if I take the negative 11x plus 3 and set it equal to 0, because I'm trying to figure out what number for x I would plug in that would make it 0. So I can subtract over my 3, so I have negative 11x equals negative 3, divide by negative 11, so my x is going to be 3/11ths. Okay, so for this one, I know that that function, because it's dividing, it's going to look like a reciprocal function because it has one function over another function. So it's going to take on my reciprocal function, but my asymptote is going to be at 3/11ths, which is the same thing as like 0.27, repeating. So here I am, we'll pretend this is 0.27. So here's my asymptote. So then I would have my graph just like this. So looking at this, because I started with two continuous functions and I now have a reciprocal function, because when I divided them, so the one function over the other function gives me a reciprocal function, and I know that reciprocal functions are continuous even though they have the asymptote, because it's in their nature to have an asymptote. So it doesn't matter where it is, but I still just have like the one asymptote, so it looks just like this. So this would be continuous, okay, because it follows all of my rules. So because I started with two continuous functions, even though I divided them and ended up getting an asymptote, it looks like a reciprocal function. A reciprocal function has an asymptote, so that's okay. So it is still just going to be continuous, okay? All right, then my other question, it says, what about trig functions? Are they continuous? So if we think about those, sine and cosine, we know that those are going to be continuous, because those are just going to be, I know that if I were to draw sine, I could go on and on and on forever. So sine and cosine, I don't have to worry about any asymptotes or anything, but sine and cosine, those are going to be continuous. Okay, so then if I were to go ahead and draw myself, so this was sine, so I'm going to draw in cosecant. Okay. So remember, cosecant, I base it off of sine, and it's going to be these u's right here. So I would have all of these u's. So even though the cosecant function is these u's right here, it's part of its nature to have the asymptotes, so it's going to be continuous, okay? So it's so unless I were to add like a whole, or add an extra asymptote, or add like a jump discontinuity, or add some like oscillation or something weird, if it looks like how it's supposed to look, like what its fundamental nature is, then it's continuous, okay? So we know sine, cosine, cosecant, secant, and even tangent and cotangent with their asymptotes, that's the way that those functions are made, so they are going to be continuous, okay? So all of our trig functions are continuous, okay? Okay. Okay, so then we already talked about like adding, subtracting, multiplying, dividing functions. So what about if I want to use like composition of functions? I want to put one function inside another function, like the f of g, the g of f, that kind of stuff. So those are also going to be continuous, just depending on each one. You have to just look at each one case by case. But in order to figure it out, it says if f is continuous at c, okay, so I have some first function. So if f is continuous at some point c, so on your first function, if it's continuous at a certain point, and then on your second function, on your g, if it's continuous at whatever that f of c value is, then you know that your f of g or g of f function is also going to be continuous. okay? So you just have to look at your first function, and if it's continuous at a certain point, and then, so first function, look at like whatever that x value is, if it's continuous, and look at the y value there. So at some c value, you have a y value. And then on the second function, if you look at the y value from the first function, if it's continuous there, then you're good to go, okay? So the first function, look at a specific x value, see what the y value is there, then take that y value and look on your second function, and if it's continuous at that y value on the second function, you know that you're gonna be continuous everywhere, okay? So when you put the function inside the function, it's gonna be continuous, okay? Okay, so then it says, we have some examples to talk through these. So it says, show that the following functions are continuous over their natural domain. So that's a good word that I should have been using all along when I was trying to talk about like reciprocal functions and trig functions. So they're natural domains. So naturally how the function occurs, if it looks like that, then you're good to go. So if it's not natural, if you add some sort of asymptote or add some sort of hole or something like that, then it would be not continuous. But it's continuous if it's over their natural domain, if it looks like what it should look like. Okay, so for my first example, I'm given the f of g, and we'll go ahead, we'll figure out what our f of x function and our g of x function might be, and then talk about those individually, and then we'll talk about it as one. So for this first one, I have, let's see, so the f of g of x is equal to the absolute value of x minus 2 over x squared minus 2. So I know that whatever letter is second is the one that's going inside, because you put this one into that one. So I could say that my g of x function is x minus 2 over x squared minus 2. And then my f of x function, I could say it's just the absolute value of x. Okay, so then thinking about these, they're natural domains. Okay, so the absolute value of x, I know that that's just going to be this v-looking graph. So the domain of this one is going to be negative infinity to positive infinity. Then this one up here, let's go ahead and factor this to figure out exactly. I know it's going to be a reciprocal function because it's one function divided by another function, but I want to figure out exactly where my asymptotes are going to be. So to do that, I want to factor my denominator. So I still have x minus 2 on the top. Now down here on the bottom, I could say x minus the square root of 2, and then x plus the square root of 2. Because when I FOIL that back out, that's going to give me x squared minus 2. Okay, so this is the same function over here. Nothing's going to cancel out or anything, I just rewrote it. But now knowing this, I know that the holes in my graph, or where my asymptotes are going to be, like where those breaks are going to be, is going to be where I would, where it would be equal to 0 in my denominator. So I know that my domain for g of x, I'm going to have the breaks at positive square root of 2 and negative square root of 2. So my domain for g of x, I could say negative infinity to negative square root of 2, and then I also have negative square root of 2 to positive square root of 2, and square root of 2 to infinity, just because I have those multiple breaks. Okay, so I would have a reciprocal function that would look something like, so negative square root of 2, positive square root of 2, so I'd have some asymptotes like so, and then I would have a function like this, and then I'm not sure exactly what's going on in the middle, it might look something like that, okay? So it would look like I have a reciprocal function with the 3 pieces. I think it'd look exactly like that, okay? So going off of that, I have my domain of negative infinity to positive infinity is my natural domain of my absolute value of x. My natural domain of this function is going to be this right here. Now, if I put them together, I have this graph, it's the red lined one over here. If I look at this graph real closely, I can see, even though it looks kind of wonky, it's a weird looking graph, but I have two asymptotes, one going up right here and one going up right here. And those are actually at negative square root of 2 and positive square root of 2. Okay, so that one, it has the same asymptotes as what I have over here. So it would be continuous as well. So even though I have asymptotes and it kind of looks like a weird function because it's a reciprocal function and an absolute value function, like smushed together. So it's a weird function, but because my domains are the same, like you can see I go out negative infinity to positive infinity, but then I have the asymptotes, which are the same as what I had before. So I would say that this is going to be continuous. And then if I look at this other one, I have the same thing. So we have a f of g of x. Is equal to, so f of g of x is equal to my absolute value of x sine of x over x squared plus 2. So again, I can break this down. So my g of x is going to be my function I put inside. So I'd have x sine of x over x squared plus 2. And then my f of x is going to be the absolute value of x. So then, if I were to think about these domains, if I actually just plug this one into the graphing calculator, I find out that my domain is from negative infinity to positive infinity. And then my absolute value, that also has a domain of negative infinity to positive infinity. So those have the same domain. Those are my domains, my natural domains that I'm starting with. And then when I put the one function inside the other function, I get this graph right here, which it's going to keep going out, and its domain is from negative infinity to positive infinity. So there's no asymptotes, no nothing weird. So this one is also going to be continuous. Okay, so I can say that this one is continuous. Okay, so whenever you're dealing with like the composition of functions, the f of g, g of f, that kind of stuff, first break it down and look at each function individually and look at each of their domains. And then look at the function overall, the composition of one, and then figure out the domain of that one and compare them, and then figure out exactly like if it's going to be continuous or not. Okay, so that's the way you approach those ones. Okay, so then kind of jumping back to limits, but still talking about continuity. So it says limits of continuous functions. So this is when we're using the composition of functions. So it says the limit as x approaches some c value of f of x is going to equal some constant, some number b. And g is continuous at the point g. So if that's the case, then we can conclude this right here. So if we have two functions, so our composition of functions, your limit there is going to be the same thing as like your g of the b. So when you plug c in, so if you plug c in to your f of x equation, you get some number b. And then if you plug b into your g equation, you get some number, and then overall that would be your answer. Okay, or just long story short, just plug in whatever you're given in for your x's or in for your thetas or whatever it is to solve. So that's all you have to do with that one, is just plug in the number and solve it out. Okay, so for this one, I have the limit as x approaches pi over 2 of cosine of 2x plus sine of 3 pi over 2 plus x. Okay, so all I'm going to do is plug my pi over 2 in. So I'd have cosine of 2 times pi over 2 plus sine of 3 pi over 2 plus pi over 2. Okay, so then kind of working our way inside out. So 3 pi over 2 plus pi over 2 is going to give me 4 pi over 2, or the same thing as 2 pi. So I have my sine of 2 pi. And then over here, 2 times my pi over 2 is just going to give me pi. So pi. And then I'm going to figure that out, and then I'll take the cosine of all of that. So my sine at 2 pi is actually going to be 0. So I have pi plus 0. So I know that's just going to be pi. So I have my cosine at pi, which is going to be -1. Okay? So in terms of how that comes from the theorem, if we had just plugged the number in, so if we were to break this into two functions, so the cosine of x and then all of this as our other function, if I were to plug pi over 2 into x right here and solve that out, which I did, I came out with pi. And then if I take the outer function and use that number b, so it's like plug in the number, figure out the thing on the inside, and then your outer function, use that new value, and then that's going to give you what the limit is there. Okay, so we would end up with -1 for that one. Okay, so you just have to plug it in and solve it out. Okay, then the intermediate value theorem. So it says a function is said to have an intermediate value property whenever it takes on two values. It also takes on all of the values in between. So if you're given 2 points, you know if a function is continuous that it's going to have to go get from one point to the other. It doesn't matter if there's all these like squiggly lines in between, or if it's a straight line or whatever it is, you're going to have to go through all of those y values. Okay, so in our picture, like, so if I'm at some x value and then some y value, so I start at this point and I end at this point, it doesn't matter if I were to just draw a straight line or draw a bunch of squigglies. I know that I'm going to hit every single x value and every single y value between those 2 points, okay? Because there's an x value everywhere in between here and here, and there's a y value everywhere between here and here. So it doesn't matter what the function is actually doing, it's just saying that there are going to be those values. So a question, it says the function h of x is a polynomial. So it says if h of 6 is equal to -7 and h of 9 is equal to 2, can you conclude that h of x is ever equal to 0? So I know based off of this, it says h of 6 is equal to -7. So my x is going to be 6 and my y would be -7. So I would be, so when I'm at 6, I'm down here at -7. So I have a point here at 6, -7. Then I also have a point at 9, 2. So here I am at 9, 2. So in order for me to get from this point to this point right here, I could draw a straight line, I could curve around, whatever I want to do, whatever my function is doing, I know to get from this point to this point right here, I'm going to have all of my x values. There is some x value everywhere, and there's also some y value. So when it asks, can you conclude that the function is ever equal to 0? Well, because I cross over my x-axis, I know I'm going to have a 0. I don't know where it might be. When I drew it once, it was over here. When I drew it a straight line, it was over here. But I know that it will equal 0 at some point, okay? Because I went from my negatives to my positives. So obviously at some point I have to equal 0. Okay, so the intermediate value theorem just says that there's all those values in between. So then kind of applying it to a couple problems, it says, show that there's a root of the equation, so x cubed minus x minus 1, between 1 and 2. So to do this, we just want to plug in 1 and then go ahead and plug in 2. And if one of those values comes out to be negative and one of them is positive, you know to get from positive to negative, obviously you have to cross the x-axis. So you're gonna have a root or a 0 or an x-intercept or whatever you wanna call it, okay? So, if I have my equation, so we'll go ahead and we'll plug 1 in first. So I'm using x cubed minus x minus 1. So if I plug 1 in, I'd have 1 cubed minus 1 minus 1. Well, I know 1 cubed is 1, minus 1 minus 1. So I'd have 1 minus 1 would be 0, minus 1, so I'm going to have negative 1. And then when I plug in 2, I'd have 2 cubed minus 2 minus 1. Well, I know 2 cubed is 8, minus 2 minus 1, so 2 minus 3 is going to give me 5. So if I think about where those points are, so when I'm at 1, I'm down here at negative 1, so my x value is 1, and my y value is negative 1. And then when my x value is 2, my y value is 5. So to get from here to here, however I want to draw that line, I can draw a straight line, I could even come down, I can cross back over. But I know that for sure there is going to be a root or a 0 because I know I at least have to cross over the x-axis 1 time to get from here to here. Okay, I can cross it multiple times. It's not asking me how many times I'm going to cross. It's just asking me, is there going to be one? So yeah, there would be one, because to go from here to here, I have to cross the x-axis, so I have to have a root. Okay, so let's do the same thing with this other one. So this time I have the equation f of x is equal to the square root of 2x plus 5, and then minus 4 plus x squared. So I'm going to go ahead and plug in 0 and 2. So my f of 0 is equal to the square root of 2 times 0 plus 5 minus 4 plus 0 squared. Well, 2 times 0 gives me 0 plus 5, so I'd have the square root of 5 minus 4, which that's going to give me, if I calculate it into a decimal, negative 1.76. And then if I plug 2 in, so my f of 2, I'd have the square root of 2 times 2 plus 5 minus 4 plus 2 squared. So 2 times 2 would be 4, plus 5 is going to give me 9. So square root of 9 is going to be 3. And then I have minus 4, and then 2 squared is going to be 4. So those will cancel, so I'm just going to be left with 3. Okay, so I know that if I were to graph these, I use my graph again. So when I'm at 0, I'm going to be down at negative 1.76. And then when I'm at 2, I'm going to be at 3. So in order to get from this point to that point, so to go from there to there, I know I have to cross the x-axis. So there indeed is going to be a root. Okay, so yes, there would be a root. Okay. Okay. So then kind of the last concept of this section is just making a continuous function by adding a point. Okay, so we know, we've talked about this graph before. So if we were to take the graph of sine of x over x, that's this graph right here. So we have the graph, but there is going to be a hole because we can't divide by 0. So right here when it says, we know that the graph is continuous everywhere except x equals 0, because I have that hole there because when I plug in 0, I can't divide by 0, so I have a hole right there. Okay, so in order to make this function continuous, I would need to define that point. So at x is 0, I would need to define the point of 1, like plug the 1 in right there. So the way that I do that is I almost write like a piecewise function. So you write your equation that you're starting with, and then you say where it's not defined, so what x can't equal in your equation. And then you figure out, you calculate what number you need to plug in for your y, and then define it at that point. Okay, so it's not exactly a piecewise function because it's not, like these aren't our domains over here, but kind of looks like one, so I kind of call it that. But yeah, so to write these, we just write our equation, and then you write where it's not defined at. Then you figure out what number you need to put to fill in that hole to define it, and that number would go right there, and then you would say, this would be the y, and then this would be x. So like the point you need to plug in to define it, here's the x, like where it's gonna be, and then that's the y where it should be, okay? So in order to like define this function, so the sine of x over x, we know that our x can't equal 0, but if I were to just add an extra point to this graph, if I were to fill in this open hole, if I were to say, put a point at 1 when x is 0, well, I would put that point right there, and I would then have a continuous function. So we can make a continuous function just by adding a point to our graph, or adding multiple points, in order to just fill in open holes, okay? So to do an example, actually, before we do the example, I got one more thing. It says, so just making our function continuous, just like what I was talking about. So it says a function, such as a rational function, may have a limit at a point where it's not defined. So if our f of c is not defined, but our limit exists, we can write the function just like this, okay? So this is just gonna be the general way you would write it. So you would write your function, and then it says if x is in the domain of f, so you would write where it's not defined, so x can't equal whatever. And then this is the limit, so the y value. So this is gonna be your limit, your y value, at x is equal to whatever point it was not defined at. Okay, so that's the general way you'll write these. So write the function, write x can't equal whatever, write the limit value or the y value that you need for defining it, and then x equals whatever number you need. Okay, so now the example. So if we look, so my example down here on the bottom, it says I'm going to use x squared plus x minus 6 over x squared minus 4. So the easiest way to do this, to write our new piecewise equation and to figure out what our continuous extension is. So a continuous extension is just literally like the name of that point you're going to put in the graph to make the function continuous. Okay, so continuous extension, when you see that in your homework, all it means is the point that you're putting in the graph. Okay, so to find our continuous extension, the number you're going to need to write in your piecewise function, if you factor your numerator and denominator, and then cancel out any common factors that you can, whatever factors cancel are the numbers that you need to plug in to solve for the continuous extension values. Okay, so if we do this in this example, we have f of x is equal to x squared plus x minus 6 over x squared minus 4. So I want to go ahead and try to factor both my numerator and my denominator. So I know right away on the bottom I'm going to have x plus 2 and x minus 2. And then on the top, if I factor this, I'll have x minus 2 and then x plus 3. Well, now looking at that, I have two common factors that can cancel each other. So I'd have x minus 2 and x minus 2 can cancel each other. So I'm left with x plus 3 over x plus 2. Okay. So then we can go ahead and figure out what our function value is going to be, because we know that we're going to have a hole at whatever number in my denominator, like makes it like 0. So I know I'm going to have a hole at x equals 2. Because if I were to graph all of this, I'm going to have a hole at x equals 2. So if I plug 2 into my equation right here, that's going to give me my y value that I need for defining it in my piecewise function. So if I plug 2 in, I have 2 plus 3 over 2 plus 2. So I'm going to end up with 5/4. Okay, so then to write my actual equation, I'd have f of x is equal to, I just write my equation, so x squared plus x minus 6 over x squared minus 4. And this is x can't equal 2. Because if I have this function, there's going to be a hole at 2, because that's where those canceled out. That's where my hole would be. Okay? And then my other one, I would have 5/4 down here, because this is my limiting value, or my y value, when my x is equal to 2. Okay? So then that would be just my new function, and I would then have a continuous function with that equation right there. So this is a continuous function versus this one is not, because you have your hole at x equals 2. Okay? All right, so that is everything. I know it was really long, guys. Thanks for sticking with me. Ask me if you have questions, and remember, it's not going to be due until Wednesday. So send me your homework by Wednesday, and then make sure you do the IXL as well, okay? All right, thanks, guys.